This is the screencast solution to problem 239 of Halliday, Resnick, and Walker. So let's go first and look at the statement of the problem. There's kind of a lot of words here, so we'll break this up and do it in pieces. So we're talking about two cars, A and B, and they're both moving in the positive direction. The graph on the right is giving us the position as a function of time for car A. And let me just sort of point out, this sort of is a standard approach that Halliday and Resnick use when presenting graphs excuse me, in the homework problems. And they do it because they want to be able to give different people different values in the problem. So rather than do the vertical axes over here sort of in a normal kind of a fashion, what they do is they give this value here, this one up here that they call x sub s, the scaling value, has a value of 32. Now from there, you can go through and just count the number of grid spacings, namely, if you count 1, 2, 3, 4, 5, 6, 7, 8, gets you to 32. So that's telling you basically that each one of these horizontal lines corresponds to 4 meters. So the first thing to do is to read and sort that out, and then you can just go through, and if you want, you can just decorate your graph with those numbers. So, as I say, that just allows Halliday, Resnick, Walker to use different numbers for different people, or Wiley Plus really is what it's all about. So that's what's going on in terms of car A. Now it tells us car B starts at the origin. It's got a velocity, but then there's also an acceleration. It's a negative acceleration, and so that means it's going to be slowing down. And so then we can look, question A says, we're supposed to find what the value of that acceleration is so that the cars are side by side. So let's just go talk, make sure, as I say, one of the things that I like to do next is to see if we can run the video, so to see what is actually going on here. So again, there's part A question up there at the top. But the idea is that, well, okay, we've got an x-axis. We choose the positive direction off to the right. And then let's talk about car A. We can put car A down there at, I guess, 20 meters, and then it's going to be moving to the right. So let's just turn that on and watch. It moves along with a constant velocity given by that graph. It gets up there to, I guess, a little bit past the 32 meters when it's all done. You might notice we're not really moving all that fast here, so this is maybe not. If it's cars, they're certainly moving pretty slowly. Okay. So then what's going on with car B? Well, car B starts at the origin, the way I've got it set up there. Its initial velocity is significantly higher than car A, but it's going to be slowing down. And so the combined video looks something on the order of this. It slows down, they pass each other at some point, and then we don't know exactly what goes on. So then how are we going to sort of work through and sort of solve that problem? Well, car A is just moving with a constant speed, and in fact, we can figure out pretty much directly. It says here we're supposed to find out what's happening at t is equal to, or the cars are sort of in the same position at 4 seconds. Well, we can figure out what's going on with car A without worrying about equations at all. There's the 4-second mark. If you just draw the line up there and go across, you can see that that means car A is at the 28-meter position at 4 seconds. So then it becomes a matter of how do we get car B to be at that same point at 4 seconds. So basically, so there's the result for car A. For car B, we need the constant acceleration equation. So we go back to the equation sheet. There are the basic equations, and it's pretty clear, I think, what we want to use is this position as a function of time, because we know almost everything to go into that equation. So we'll just write that down. The initial position, as I said, is 0. Then there's an initial velocity, 12 meters per second. And then there's 1/2 at squared. Now, we're told that the acceleration is negative, so there's a choice here in terms of how you do this. We could sort of recognize that that the acceleration is going to be negative and explicitly put in a minus sign here instead of the plus. I think at this point I'll just leave it as 1/2 a sub b times t squared. And if everything works out according to plan, we should end up with a negative value for a sub b at this point. Okay, so then as I say, it's actually fairly straightforward here because we're just looking then at 4 seconds. We want to have car B at the same position as car A, namely the 28 meters. So you put in that t is equal to 4 seconds, And the only thing we don't know in this equation is the acceleration, a sub b. So first, if you just multiply these various quantities out, 12 times 4, and then multiply the 4 seconds squared and divide by 2, we get that result. And it's not too much work to sort of recognize, move the 48 over to the other side. And then we end up with the acceleration equal to minus 2.5 meters per second squared. So again, it comes out negative the way they had sort of let us know that that would be happening. So that's good, that's sort of a check that things are working right. Let me remind everybody the units here all work out. Is quite, nice if you're careful with it, that everything sort of comes out to give you meters divided by seconds squared. And so it's, again, a way to check to make sure that your algebra is working out okay. So that's the answer to part A. Let's go back and look at the problem because, as I say, a lot of words in this problem. So here it says for part B, for that value of A, how many times are the cars side by side? So that's a little bit confusing. Part C actually says to sketch the position, and that wasn't part of the Wiley Plus because they can't have you sketch results for Wiley Plus. But then it also says here, if the acceleration is larger or smaller, how is that going to change? So let's just go back and think a little bit more about what this motion, actually what the video kind of looks like, if you will. So remember, here's our car A on top, car B a little bit below, and the motion that was going on is that these guys came and they passed each, or they came to the same position, presumably there at the 4 second point. So that's the picture, but it's not the only possibility of how things might work. Or we can sort of ask, all right, what's going to happen in terms of the speed of these cars? So we know the speed of A is constant, but the speed of B is given, of course, by the constant acceleration equation. And so as t increases, the velocity gets smaller. And in fact, it would even go negative if we went far enough. So let's just think about then the velocity for this motion. I'll just run it again. The velocity is decreasing. And so let's try to draw a graph then of this motion of the car B. We've already got the graph of car A up there on the top. And when we do that, then we're going to end up with, again, the velocity starts off, the car starts at the origin down here, and it starts off with a certain velocity heading off that direction. And notice the slope of that line there is steeper than the slope of the line for car A, so it's clear it's moving at a higher velocity. But the fact that there's a negative acceleration means the car is slowing down, and that means we don't just move in a straight line. I suppose if the velocity just was constant, it would go off like that, and clearly those two cars would be in the same position at about 2.5 seconds, I guess. But because of the fact that the velocity is decreasing, the curve bends over, and the way I've drawn it here is sort of what the picture looked like. Namely, let me see if I can run the video again. There it is. It looks like they kind of catch up to each other, but then car B continues to slow down, and so car A continues to move ahead. So there, as I say, is that picture that we had drawn there. That looks like they sort of just come together right at that point, but then because car B is slowing down, car A kind of moves on ahead. So that's one possibility. I guess we get to watch it one more time. But let's think about another possibility, which corresponds to car B accelerating, or decelerating, if you will, not quite so quickly. Or the way I've got the image shown here, it's actually going to move a little faster, I think. Notice car B is still moving ahead and slowing down. I'll run it again for you. But it's moving fast enough that it passes car A. And then eventually, though, car A catches up again because car B continues to slow down. So that motion we would graph according to the red curve that's here, the dotted red curve, where we've got this setup where the velocity starts out the same, but the acceleration is presumably smaller. And so what happens is when you get to this point here where the two cars are at the same position, there's a difference now that the velocity of the car B, that's the dotted red curve, is greater than the velocity of car A, right? Because it's moving past car A, so it's got a higher velocity. On the other hand, when you get over here, the velocity of... don't know why that's happening, but the velocity of car B is now less than the velocity of car A. So that's two different places where the curves are at the same place, car B and car A, but the velocities are different. If we go back to our other curve, the blue curve, if you're looking at this in color, that's the one that we had worked out initially, where the cars sort of reach the same position here at 4 seconds. And here you can see that the two velocities are actually the same. So we've got three different possibilities. We can have when the cars sort of are at the same position, they could be traveling with the exact same velocity. Car B could be traveling more quickly, in which case it's this situation and it's going to be moving past car A. Or it could be traveling with a velocity that's smaller, which means it's already past car A and we're moving backwards in the, car A is now moving ahead of car B at that particular time. So what's happening here? Well, what we need to do then is just figure out what is the velocity of car B at this point corresponding to 4 seconds, because that's the problem the question we're interested in. So if we just plug in that number, t is equal to 4 seconds, and calculate it, it comes out to be 2 meters per second. Well, in fact, that's exactly the same as the speed of car A. I guess we haven't done this yet, but if we look, say, from 0 to 2 seconds, car A has increased its distance by 4 meters, and that's been 2 seconds. So, in fact, the velocity of car A is 2 meters per second as well. So that tells us that this condition we solved for in part A is exactly this one represented by the blue curve, namely that the two cars are traveling at exactly the same speed at the point where they come together, to come to the same position. And then, of course, what's going to happen is that car B is going to continue to slow down. Car A will sort of move ahead. So it's closer to that first simulation that I gave you. Now, this is really just that Halliday and Resnick picked the numbers to make this happen. If the acceleration is a little bit less, then we're going to get this result that we see in the dotted red curve up here. If the acceleration is a little bit greater, well, that means that this curve is probably that the car B is going to slow down more quickly, and it may not even catch A. So I think I've got a simulation of that, and you can see here that car B is slowing down such that it never actually reaches and never gets to the same point as car A. And that's represented then by this blue curve here that says, well, yes, the velocity starts out, but the acceleration is high enough that it never actually gets to the same position as car B. So that then is the answer to those last parts C and D about the acceleration. If the acceleration is a little smaller, it's gonna intersect the curve twice. If it's a little bigger, it's not going to intersect the curve at all. So hope that sort of helps clear up that problem.